Welcome, everyone, to another journey of science, to sleep by through the quiet wonders of the cosmos. Tonight, as you relax, let your mind drift into the deep stillness of space, where science and imagination meet. We're going to explore a question that has fascinated scientists, philosophers, and dreamers alike. What is spacetime really? You've heard the word before, spacetime. It sounds almost mysterious, like a hidden fabric weaving together the stars, the planets, and even us. But what does it actually mean? Is it just a stage where events unfold? Or is it something much more alive, bending, stretching, and shaping the universe itself? Together, in this quiet hour, we'll walk slowly through the ideas of Einstein and beyond. We'll look at space, time, gravity, and the deep mysteries that connect them. And as we do, I invite you to let the words wash over you, calming your thoughts, easing your breathing, and helping you settle into rest. So, find a comfortable spot, close your eyes if you'd like, and let's begin this journey into the fabric of reality itself, into the mystery of spacetime. When we hear the word spacetime, it can sound like something pulled straight from a science fiction novel, something mysterious and abstract. Yet, at its core, spacetime is one of the most fundamental concepts of modern physics. It reshaped the way we think about the universe itself. Before Einstein, space and time were thought of as two completely separate things. Space was the arena, the three-dimensional stage in which events played out, while time ticked away in the background, unaffected by anything happening in the world. The great thinkers of the past, from Newton to Galileo, treated space as a kind of eternal and changing backdrop, and time as a river that flowed at the same pace for everyone, everywhere. But the revolutionary insight that came in the early 20th century shattered this view forever, and in its place was born the concept of spacetime. To begin to understand it, imagine space itself. Picture the room you are in right now. You can describe its dimensions, its length, width, and height. These three measurements give you the coordinates to locate any point inside it. Now add time, the flow of moments, the ticking of the clock on your wall, or the beating of your heart. Together, these form four coordinates, 3 for space, 1 for time. At first glance, this might seem trivial. Of course, we need both space and time to describe where and when something happens. But Einstein's genius was in showing that these are not two separate things joined together for convenience. They are fundamentally one and the same, woven into a single four-dimensional fabric, spacetime. This was not just a mathematical trick. It was a deep shift in understanding. Space and time cannot be peeled apart. You cannot describe an event fully by stating where it occurred without also saying when. Nor can you mark the passage of time without some reference to space. Every action, every particle, every star's light, every movement exists inside this unity. To imagine the universe without spacetime is impossible, because spacetime itself is the framework that allows reality to exist. One of the most powerful ways to visualize this unity is to think of your own journey through life. From the moment you were born, you have been moving, not just through space, but also through time. You may stay still in your chair, moving very little in space, but every second, you advance 1 second further into the future. You cannot pause it. You cannot step out of it. Your life is not a series of dots scattered randomly, it is a line drawn across spacetime. A path scientists call a world line. Everyone and everything has a world line. The Earth circling the sun orbiting the center of the Milky Way, even the galaxies drifting apart as the cosmos expands. All of these motions are stitched into the tapestry of spacetime. When Einstein first proposed this idea, it seemed almost impossible to grasp. For centuries, the belief was that space was absolute, a vast emptiness that did not care what happened within it, and that time was a universal metronome, ticking away uniformly across the cosmos. But Einstein's special theory of relativity revealed that this was an illusion. Observers in different states of motion do not agree on time. They do not even agree on distances. Time stretches and contracts. Lengths shrink and expand. And yet, there is a deeper unity beneath these changes. Spacetime itself remains consistent. This was a profound discovery, because it told us that what we experience as space and time are simply perspectives, slices of a larger whole. Think about the speed of light, that cosmic speed limit which nothing in the universe can surpass. Why is it constant? Why does every observer, no matter how fast they are moving, measure the same speed for light? The answer lies in spacetime. The constancy of light's speed is not a random coincidence. It is a clue that space and time are woven together in such a way that they adjust themselves depending on your motion, ensuring that the balance of spacetime is preserved. Your time might slow down compared to mine. Your distances may shrink compared to mine. But the laws of spacetime guarantee that the underlying reality remains coherent. This unity between space and time also means that the universe does not truly have a universal now. It may feel, in your daily life, that there is a single present moment stretching across the cosmos, as though time is synchronized everywhere. But relativity tells us otherwise. For someone moving relative to you, what they consider now may not align with your own. Events that seem simultaneous to you may not be simultaneous for them. In this sense, the present is not a single universal slice, but rather a local perspective carved out of spacetime. What exists, then, is not a moving present moment, but the entire four-dimensional structure, past, present, and future, all part of the same cosmic fabric. It can be unsettling to realize that time, as we experience it, is not absolute. Yet it is also deeply calming in a strange way. For within the concept of spacetime, every event, every memory, every heartbeat, every sunrise, is permanently etched into the structure of the universe. Nothing truly vanishes. It becomes part of the grand geometry of reality. Now, to imagine spacetime, many scientists and educators turn to the metaphor of a fabric or a sheet. This is a simplification, of course, because spacetime is four-dimensional, not two. But the image can be useful. Picture a large rubber sheet stretched tight. Place a ball on it, and the sheet bends under its weight. This bending represents what mass and energy do to spacetime. The sheet is not just a stage for the ball, it responds to it, shaping its motion. This metaphor prepares us for the deeper realization that spacetime is dynamic, alive in its own way. It curves, it ripples, it carries the imprint of everything that exists. But even before diving into how it bends and stretches, it's important to pause and appreciate the sheer audacity of the idea. To take space and time, two concepts so ingrained in human experience, so natural to separate and show that they are one, inseparable, interdependent, was to change our place in the cosmos forever. Einstein did not simply tweak Newton's laws. He redrew the map of reality itself. If you think about the night sky, the stars glowing faintly in the darkness, the light you see is a record of spacetime structure. A star hundreds of light years away is not just far in space, it is far in time. Its light left before you were born, traveling across the woven fabric of spacetime, carrying with it a message from another corner of the universe. In every starlight shimmer, you are seeing not just distance, but history, both tied together by the inseparability of space and time. And so, the concept of spacetime is not only a scientific revolution, it is a kind of poetry hidden in physics. It tells us that we are not drifting in emptiness, nor counting time in isolation. We are threads in a fabric so vast that it holds galaxies, black holes, and perhaps the secrets of existence itself. It tells us that our lives are not simply fleeting moments, but curves drawn into the geometry of the cosmos, each one part of the universe's grand design. When we think of space, our minds often go to the vast darkness above us, the night sky dotted with stars, the mysterious expanse that begins where Earth's atmosphere ends. It is natural to imagine space as emptiness, as nothing at all, a void waiting to be filled by planets, moons, and galaxies. Yet science has shown us that space is far more than a silent backdrop. It is not just the container in which matter exists, it has structure, it has geometry, and it plays an active role in shaping reality. To speak of the nature of space is to move beyond the idea of a hollow vacuum and to recognize that space itself is something real, something fundamental, something that can bend, stretch, ripple, and expand. In the simplest sense, Space is the arena of existence. It provides the coordinates that let us describe position and orientation. Imagine your bedroom at night, quiet and still. You can describe where your pillow is, where the lamp rests, where the window lies. You might not think of it this way, but what you are really doing is mapping positions onto the three dimensions of space: length, width, and height. Without those dimensions, there would be no way to describe where. Objects would have no relation to one another. And yet, the idea that space is simply a background, a grid, is misleading. Space is not a passive framework. It interacts with the contents it holds. For thousands of years, philosophers debated whether space was real or just a way of thinking. Some argued that space was absolute, a fixed arena existing independently of matter. Others believed that space had no existence without the objects inside it, that it was only the relationship between things. Newton, for example, believed in absolute space, an unchanging stage upon which the drama of the cosmos unfolded. Leibniz, his contemporary, argued that space was nothing more than the ordering of objects relative to one another. These debates were not merely academic. They reflected fundamental questions. Is space something, or is it nothing? The discoveries of modern physics tipped the balance firmly in favor of space as something real. With Einstein's theories of relativity, it became clear that space is not fixed, not absolute, not immutable. It bends in the presence of mass and energy. It can expand over cosmic time. It can vibrate with ripples that we call gravitational waves. These properties mean that space is not emptiness. It is a medium with its own dynamic qualities, one that responds to the universe's contents. To grasp this more intuitively, imagine space as a fabric stretched out beneath the stars. This fabric is invisible to the eye, yet it determines how planets orbit, how light travels, and how galaxies move apart. When you drop a heavy ball onto a stretched sheet, the sheet curves downward. Another ball placed nearby will roll toward it, not because the balls pull on each other directly, but because the sheet itself is curved. In a similar way, Earth orbits the Sun not because the Sun reaches out with invisible strings, but because the Sun's mass curves the space around it, guiding Earth's path in a natural arc. This is not just an analogy, it is the very essence of what space is. But space is not limited to the grand scales of stars and galaxies. Even at the quantum level, it reveals surprising features. What seems like emptiness at tiny scales is seething with activity. Particles flicker into and out of existence, borrowing energy from the vacuum for fleeting moments. This so-called quantum foam suggests that space has a restless quality, alive with fluctuations even in the absence of matter. The very idea of empty space is, therefore, an illusion. At every scale, space has texture, energy, and reality. The most striking feature of space, however, is its ability to expand. The universe itself is not expanding into something else, it is space itself that stretches, carrying galaxies with it. Picture dots on the surface of an inflating balloon. As the balloon grows, the dots move apart, not because they are traveling across the surface, but because the surface itself is expanding. In the same way, galaxies recede from one another as space itself swells. This expansion tells us that space is not a rigid framework, but a living, dynamic entity. It evolves. It changes. It carries the history of the cosmos within its fabric. When we look at the night sky, we see light from distant galaxies that has traveled for billions of years across this expanding fabric. That light is stretched as the universe expands, its wavelengths lengthening, its color shifting toward the red. This redshift is direct evidence that space is not passive. It is shaping the very information that reaches us. Each photon of light is like a messenger, and by studying how it changes on its long journey, we learn about the properties of space itself. It is worth pausing to consider just how radical this view is compared to what our senses tell us. To the human eye and mind, space feels like nothingness. You cannot touch it, cannot scoop it into your hands, cannot see it directly. Yet physics insists that it is more than absence. It is something that influences motion, bends paths, stores energy, and expands across time. The challenge of grasping this lies not in the science, but in the limits of our intuition. We evolved to navigate the scale of trees and rivers, not galaxies and quantum fields. Space as a dynamic, flexible fabric is not natural to imagine, but it is what reality demands of us. Even within our solar system, space reveals its subtle influence. The orbit of Mercury, closest to the Sun, deviates slightly from what Newton's laws predicted. For decades, this puzzled astronomers. The solution came when Einstein showed that space around the Sun was not flat, but curved. Mercury's path was not broken, it was following the curve of space itself. That small correction became one of the first triumphs of general relativity, proof that space is not inert. It is active, and its geometry determines the motion of worlds. In the modern era, we have gone further. We have measured the ripples in space itself. In 2015, scientists detected gravitational waves for the first time, tiny vibrations in the fabric of space created by the collision of black holes billions of light years away. These waves pass through Earth, stretching and squeezing space by distances smaller than a proton, yet still detectable by our instruments. This achievement confirmed beyond doubt that space is not emptiness. It is a medium that can be shaken, disturbed, and rippled by the most violent events in the cosmos. To speak of the nature of space. Then, to recognize it as both the stage and the actor, both the container and the content. It is the canvas on which the universe is painted, but also part of the painting itself. It does not simply exist independently of matter and energy, it interacts with them, is shaped by them, and in turn shapes them. To call space a void is to miss its richness. It is more like a hidden architecture, unseen, yet essential, a web that underlies every star, every galaxy, every particle, and even the flow of time itself. Time is one of the most intimate experiences we have as human beings. We feel it passing in every heartbeat, in every sunrise and sunset, in the changing of the seasons, in the gradual aging of our bodies and faces. It feels so familiar, so obvious, that we rarely stop to question what it truly is. Yet when we ask, what is time? We find ourselves facing one of the deepest mysteries of science and philosophy. Time is the invisible thread that ties together our experiences, and yet it resists every attempt to pin it down. Physicists treat it as a dimension, mathematicians describe it with equations, philosophers wrestle with its meaning, and we all live within it, unable to step outside. To understand spacetime, we must understand not just space, but the nature of time itself. Our everyday sense of time is linear. We experience moments one after another, like beads on a string, flowing from past to present to future. We cannot return to a moment once it has passed, nor can we leap ahead to one that has not yet arrived. The present moment feels unique, a constantly moving now that sweeps us forward. This sense of flow is so deeply ingrained in human consciousness that it feels undeniable. Yet physics complicates this picture in surprising ways. In equations describing the fundamental laws of nature, time does not flow. It is treated as just another coordinate, alongside the dimensions of space. Think of how we describe an event, not only by where it occurs, but when. If you tell a friend to meet you at a cafe, you must provide both the location and the time. Without both, the event cannot happen. This is why time is treated as a dimension, because to fully describe reality, we need it as much as we need length, width, and height. In this view, the universe is not a film reel being played, with each moment blinking into existence and then disappearing. It is more like the entire reel itself, with every frame past, present, and future existing together as part of a larger whole. Physicists sometimes call this the block universe, where time is laid out as a dimension of spacetime, with all events fixed in their place. But if time is just another dimension, why does it feel so different from space? Why can we move freely forward and backward in the three dimensions of space, but only forward in time? This asymmetry is one of the great puzzles of physics. In the equations of motion, time can go forward or backward equally well. But in our lives, time has an arrow, it always points from the past toward the future. The explanation may lie in entropy, the measure of disorder. According to the second law of thermodynamics, entropy in a closed system tends to increase. A glass shatters, but does not reassemble. Smoke disperses, but does not gather back into a neat cloud. This increase in disorder gives time its direction, its irreversible quality. The arrow of time emerges not from the fundamental equations themselves, but from the way the universe evolves from order to disorder. The strange thing is that while time feels universal to us, Einstein's theories of relativity show that it is not. Time is not absolute. It is not the same for everyone, everywhere. Instead, time is elastic, bending and stretching depending on speed and gravity. For someone moving close to the speed of light, time slows down relative to someone at rest. This is not a trick of perception, it is a measurable reality. Astronauts orbiting Earth experience time slightly more slowly than people on the ground. This effect has been confirmed using ultra-precise atomic clocks on airplanes and satellites. When one clock flies around the world and returns, it shows a tiny but real difference compared to the clock that stayed behind. Time itself has flowed differently for the two clocks, simply because of motion. Gravity, too, affects time. Near a massive object, such as Earth, time passes more slowly than farther away. This effect is called gravitational time dilation. Without accounting for it, our GPS systems would fail within hours. The satellites orbiting Earth experience slightly faster time than we do on the surface, and the corrections for this are built into their calculations. What this means is that time is not universal, not a single ticking rhythm across the cosmos. It depends on where you are and how you are moving. There is no single cosmic clock that defines the present. Each observer carries their own clock, and all are correct within their own frame of reference. This relativity of time leads to profound consequences. Imagine twins. One stays on Earth while the other travels at near light speed to a distant star and back. When the traveling twin returns, less time has passed for them than for the twin who remained behind. This is known as the twin paradox. Though it is no paradox at all, it is a natural outcome of relativity. In this way, time itself can be stretched and compressed. It is not fixed and universal, but malleable, woven into the fabric of spacetime. Another mystery of time is the way it connects us to the past and future. We remember what has happened but cannot recall what is yet to come. Our memories flow backward, but our hopes and predictions stretch forward. Why should time favor memory in one direction? Physics itself does not explain this directly. The equations do not distinguish between past and future. The explanation may again lie in entropy. The past is more ordered, and therefore it leaves records, footprints, fossils, photographs, and memories in our minds. The future, being more disordered, has no such records. This is why we can know the past, but not the future. Time also touches on the question of free will. If all events exist in the block universe, if the future is already laid out as firmly as the past, then do we truly make choices? Or are we simply following a path already inscribed in spacetime? Some scientists and philosophers accept this deterministic view, while others argue that quantum uncertainty leaves room for openness, that the future is not yet written. The nature of time sits at the center of these debates, and there is no final answer. At the cutting edge of physics, time itself may not even be fundamental. Some theories suggest that time emerges from deeper, more basic processes. In quantum mechanics, time is treated differently than in relativity. Attempts to unify these two great pillars of physics, relativity and quantum theory, have led to ideas where time itself might be an illusion, a convenient parameter we use to describe change, but not something fundamental. This is a startling possibility, because it challenges the very foundation of our experience. And yet, whether time is fundamental or emergent, illusion or reality, it shapes everything we know. Stars live and die across millions of years. Galaxies form, collide, and transform. Our own lives unfold across decades, marked by beginnings, changes, and endings. Time is the thread that turns chaos into story, that allows cause to follow effect, that lets us find meaning in the sequence of moments. For all its mystery, time remains the most personal dimension. Space may stretch far beyond what we can imagine, galaxies beyond counting, voids larger than anything we can cross. But time touches us intimately. It is in the beating of the heart, the rhythm of the breath, the steady march of days. It is in the way we age, the way we grow, the way we move from childhood to adulthood to old age. Space may tell us where we are, but time tells us who we are. When people first hear that spacetime is like a fabric, the image that often comes to mind is a vast, dark sheet stretched out under the stars, invisible yet all-encompassing. This metaphor, though simplified, offers a doorway into one of the most profound ideas of modern physics, that space and time are not rigid, static, or passive, but instead flexible and dynamic, capable of bending, stretching, rippling, and reshaping themselves in response to the matter and energy they contain. To speak of the fabric of spacetime is to move beyond the classical view of space as emptiness and time as a clock, and to embrace a vision of the universe as an interconnected, living geometry. Einstein's general theory of relativity, published in 1915, revealed that spacetime is not a silent stage where cosmic events unfold but an active participant in those events. His insight was astonishing. Gravity is not a mysterious force pulling objects together across empty voids, but the manifestation of curved spacetime. Mass and energy tell spacetime how to bend, and that bending tells objects how to move. What we perceive as the pull of gravity is simply the result of following the natural paths, called geodesics, through a warped geometry. In this picture, spacetime becomes the hidden architecture of the cosmos, an invisible scaffolding that determines the orbits of planets, the paths of light, and the fate of galaxies. To visualize this bending, imagine a large rubber sheet stretched tight. If you place a heavy ball on the sheet, it sinks slightly, distorting the surface. Now roll a smaller ball nearby. Instead of traveling in a straight line, it curves inward, circling around the heavier ball. The smaller ball is not being pulled by an invisible tether, it is simply following the contours of the curved sheet. Replace the rubber sheet with spacetime, the heavy ball with a star or planet, and the smaller ball with a planet, moon, or even a photon of light, and you have the essence of general relativity. The geometry of spacetime guides motion in ways that defy the intuition of Newtonian physics. But unlike a rubber sheet, spacetime is not two-dimensional. It has 4 dimensions, 3 of space, and 1 of time woven together. The curvature that Einstein described is not something we can see with our eyes, because it exists in this higher dimensional fabric. Yet we can observe its effects in countless ways. The orbit of Mercury, for example, puzzled astronomers for decades. It deviated slightly from predictions based on Newton's laws. Einstein's theory explained this perfectly, showing that the Sun's immense mass curved spacetime in such a way that Mercury's orbit precessed or rotated over time. That tiny but measurable effect was one of the first confirmations that spacetime truly behaves like a fabric that can be shaped. Another striking consequence of curved spacetime is the bending of light. Normally, we think of light as traveling in straight lines, the fastest path between 2 points. But in the presence of massive objects, such as stars or galaxies, spacetime curves, and light follows those curves. This phenomenon, called gravitational lensing, allows massive clusters of galaxies to act like cosmic magnifying glasses, distorting and amplifying the light from even more distant galaxies behind them. Through these natural lenses, astronomers can peer deeper into the universe than would otherwise be possible. The very fabric of spacetime, bent and curved by gravity, becomes a tool for exploration. Spacetime is not just curved, it can ripple. In 2015, a century after Einstein predicted them, gravitational waves were directly detected for the first time. These are literal vibrations in the fabric of spacetime, created when massive objects like black holes or neutron stars collide. The waves spread outward at the speed of light, carrying with them information about the violent events that generated them. The detectors that observed these waves had to measure changes smaller than a fraction of a proton's width, because the stretching and squeezing of spacetime is so subtle by the time it reaches us. And yet, Those tiny signals carry with them the story of cosmic cataclysms billions of years away. To detect gravitational waves is to listen to the universe's deepest whispers, vibrations in the very fabric of reality. The fabric of spacetime also stretches on cosmic scales. The expansion of the universe is not galaxies flying apart through pre-existing emptiness, it is space itself expanding, carrying galaxies with it. As spacetime expands, the distances between galaxies increase, even if the galaxies themselves are not moving through space. This cosmic stretching leaves fingerprints in the light we observe. The wavelengths of photons traveling across the expanding universe are stretched as well, shifting them toward the red end of the spectrum. This cosmological redshift is direct evidence that the fabric of spacetime is dynamic, capable of changing across billions of years. The universe is not a static arena but a restless fabric, unfolding in ways that continue to surprise us. Perhaps the most extreme manifestations of spacetime fabric are black holes. These are regions where spacetime curves so intensely that not even light can escape. To an outside observer, the edge of a black hole, known as the event horizon, marks a boundary beyond which nothing can return. Yet inside, the fabric of spacetime is distorted to such an extent that the familiar rules of time and space seem to break down. The singularity at the center of a black hole represents a place where our current understanding of spacetime reaches its limits. Here, the equations of relativity suggest infinite curvature, but physicists believe that quantum effects must somehow resolve the paradox. Black holes, therefore, are not just exotic objects in the sky, they are laboratories that test the very nature of spacetime fabric under extreme conditions. On the other side of speculation lies the idea of wormholes, hypothetical tunnels through spacetime. If spacetime is a fabric, then in principle, might fold or connect distant regions in ways that provide shortcuts, bridging vast distances, or even different universes. Wormholes are allowed mathematically by Einstein's equations, though whether they exist in nature is still unknown. They capture the imagination because they suggest that spacetime is not just a passive container, but a malleable, complex structure with possibilities beyond ordinary travel. The very idea hints that the fabric of spacetime might be richer and stranger than even Einstein imagined. Even at the smallest scales, the nature of spacetime fabric is uncertain. Quantum physics suggests that spacetime may not be smooth and continuous at all, but grainy and fluctuating, like foam. At scales unimaginably smaller than atoms, spacetime may boil with constant activity, popping and bubbling in ways that challenge our classical notions of fabric. This quantum foam might hold the key to unifying relativity with quantum mechanics, two frameworks that describe different aspects of reality, but remain incomplete when combined. Some theories suggest spacetime itself could emerge from even deeper structures, like networks of quantum information or entangled states. If so, then the fabric we speak of may not be fundamental, but a tapestry woven from threads we cannot yet see. And yet, despite these mysteries, we can see the evidence of spacetime fabric all around us. In the motion of the planets, in the bending of starlight, in the expansion of the cosmos, in the ripples of gravitational waves, spacetime reveals itself not as nothingness, but as a dynamic stage that both shapes and is shaped by the universe. It is invisible, intangible, and yet it is as real as the ground beneath our feet. Without it, there would be no trajectories, no orbits, no history of the cosmos unfolding. The universe is not painted onto spacetime, it is stitched into its very threads. Gravity is something we all feel in the most ordinary and intimate ways. It is the force that anchors us to the ground, that makes a ball fall when we drop it, that pulls raindrops toward the earth, and that governs the tides of the oceans as the moon circles above. For centuries, gravity was described as an invisible tug, a force of attraction acting between masses across empty space. This picture, given to us by Isaac Newton, was a triumph of human thought and worked beautifully for predicting the motions of planets and the falling of apples alike. But Einstein's general theory of relativity revealed something even deeper. Gravity is not a force in the traditional sense at all. It is geometry. It is the bending and warping of spacetime itself, a reshaping of the stage on which the universe unfolds. To grasp this, we must first return to Newton's picture. Newton imagined that every mass in the universe pulls on every other mass with a force proportional to their sizes and inversely proportional to the square of the distance between them. This simple law explained why planets orbit the sun, why the moon orbits Earth, and why you remain grounded. But it left questions unanswered. How does the Earth know the sun is there, 93 million miles away, and feel its pull instantly? How does this invisible influence travel across empty space? For Newton, it was enough to describe how gravity worked, without needing to explain why. Einstein dared to ask why. He realized that Newton's vision of instant action at a distance did not fit with the constancy of the speed of light, the absolute limit set by special relativity. If nothing can travel faster than light, how could the sun's gravity reach Earth instantaneously? The answer came when Einstein reimagined gravity not as a transmitted force, but as the natural result of curved geometry. Mass and energy do not reach out and pull. Instead, they bend spacetime around them, and objects move along the curves of this geometry. What we feel is weight, what we see as orbits, what Newton described as force, are all simply the consequences of following paths through curved spacetime. A common way to visualize this is to imagine spacetime as a stretched fabric. Place a heavy object, like a bowling ball, on the fabric, and it sinks down, creating a well. If you then roll a smaller ball nearby, it will spiral inward, circling around the heavy ball. Not because it is being pulled, but because the surface itself is curved. The smaller ball is simply following the straightest possible path, called a geodesic, across the distorted geometry. In our universe, the sun curves spacetime around it, and Earth follows a geodesic within that curve. We call that orbit. To us, it looks like gravity pulling Earth toward the sun, but in Einstein's view, Earth is simply traveling along the natural path, dictated by geometry. This geometric vision of gravity reshaped physics in profound ways. It explained mysteries that Newton's theory struggled with. For example, Earth's orbit around the sun shifts slightly with each revolution, a phenomenon known as precession. Newton's laws could almost account for this, but left a small discrepancy. General relativity explained it perfectly, showing that the sun's intense gravity slightly twists the surrounding spacetime, altering Mercury's path. This was one of the first great triumphs of Einstein's theory, demonstration that gravity as geometry was not only elegant, but also accurate. The bending of spacetime does not affect only planets and moons. It also bends light itself. When starlight passes near a massive object, such as the sun, it curves along the warped geometry. This was confirmed in 1919, when astronomers observed starlight during a solar eclipse and found that the star's apparent positions shifted slightly, exactly as Einstein predicted. This bending of light by gravity, known as gravitational lensing, has since become a powerful tool in astronomy, allowing scientists to detect distant galaxies, dark matter, and even exoplanet, all by watching how light curves through warped spacetime. What once seemed like a mysterious force now reveals itself as the shape of the universe itself. One of the most striking demonstrations of gravity as geometry comes from the discovery of gravitational waves. Imagine two black holes spiraling into one another, their immense masses twisting and shaking the surrounding spacetime. The collision sends ripples outward, like waves spreading across a pond. These ripples are not traveling through spacetime, they are oscillations of spacetime itself. In 2015, detectors on Earth recorded these waves for the first time, a century after Einstein predicted them. The instruments measured tiny distortions, far smaller than the width of a proton, as spacetime itself stretched and squeezed in rhythm with the cosmic collision billions of light-years away. This confirmed that gravity is geometry in motion, not just static curves, but a fabric that vibrates and carries information across the cosmos. The geometry of spacetime also gives rise to black holes, perhaps the most extreme expressions of gravity. When a massive star collapses at the end of its life, it can compress so tightly that spacetime curves inward on itself, creating a region from which nothing can escape. The event horizon of a black hole marks the point where geodesics, the straightest possible paths, all curve inward. Even light, which normally travels straight, is forced inward, unable to escape. To an outside observer, time itself slows down near the event horizon, stretching into infinity. This dramatic warping shows that gravity is not just about pulling masses together, it is about reshaping the very fabric of reality. Einstein's insight also explains why gravity affects time. In curved spacetime, the passage of time is not the same everywhere. Clocks near massive objects tick more slowly than clocks farther away. This gravitational time dilation has been measured directly, with atomic clocks placed at different altitudes on Earth. The higher clock, farther from the planet's mass, ticks ever so slightly faster than the lower one. Though the difference is tiny, it is real and measurable, and it must be accounted for in technologies like GPS satellites. Without correcting for gravitational time dilation, your phone's navigation would quickly drift out of accuracy. What seems like an abstract consequence of geometry has practical effects woven into daily life. The idea of gravity as geometry also opens up the possibility of phenomena far beyond ordinary experience. Wormholes, for instance, are solutions to Einstein's equations that describe tunnels through spacetime, potentially connecting distant points. Whether they exist in nature is unknown, but the mathematics shows that geometry can, in principle, allow shortcuts through the cosmos. Even the expansion of the universe itself can be seen as a geometric effect, with spacetime stretching in all directions, carrying galaxies with it. Gravity, in this view, is not just local bending but part of the grand geometry that dictates the fate of the entire cosmos. At the deepest levels of physics, scientists wonder whether spacetime geometry is truly fundamental. Quantum mechanics suggests that the fabric may not be smooth and continuous, but woven from more basic constituents. Some theories propose that geometry itself emerges from networks of quantum entanglement, that spacetime and gravity are not primary, but arise from information at a deeper level. If true, gravity as geometry would still hold at large scales, but its roots would lie in something even more fundamental, a structure of reality not yet fully understood. And yet, despite all these mysteries, the geometric view of gravity remains one of humanity's greatest achievements in understanding the universe. It unites the fall of an apple with the dance of galaxies. It explains the orbits of planets, the bending of light, the ticking of clocks, and the ripples of spacetime. Gravity is not an invisible hand pulling objects together, it is the shape of spacetime itself, sculpted by mass and energy, guiding motion along curves written into the fabric of the cosmos. When we think about time, we often imagine it as a steady rhythm, a kind of universal clock that ticks the same for everyone, no matter where they are or how fast they're moving. It feels absolute because our daily experiences don't seem to reveal otherwise. We wake up in the morning, we go through our day, and the hours flow in a dependable sequence. But the deeper truth uncovered by Einstein's theory of relativity is that time is not absolute. Instead, it is relative, tied intimately to motion, speed, and even gravity. This idea reshaped not only physics, but also our understanding of reality itself. For it means that there is no single universal now shared across the cosmos. Einstein's journey toward this realization began with the principle that the speed of light is constant. No matter how fast you are moving, if you measure the speed of a beam of light, you always get the same answer, about 186,000 miles per second. This constancy may sound simple, but it creates consequences that defy common sense. If you are traveling on a highway at 60 miles per hour and you throw a ball forward at 30 miles per hour, someone standing by the road would see the ball moving at 90 miles per hour relative to them. Speeds add together, but light does not follow this rule. If you shine a flashlight while running, the beam doesn't travel at the speed of light plus your running speed. It always travels at the speed of light, no more, no less. To reconcile this strange fact, Einstein realized that time and space themselves must adjust depending on your state of motion. This leads to the phenomenon known as time dilation. When you move close to the speed of light, Time for you slows down relative to someone who is at rest. Imagine twins. One remains on Earth, while the other boards a spaceship and travels near the speed of light to a distant star and back again. When the traveling twin returns, they will have aged less than the twin who stayed behind. From the traveler's perspective, their own clock ticked normally throughout the journey, but compared to the earthbound twin, fewer years passed for them. This is not science fiction, it is a direct consequence of relativity, and has been confirmed by experiments. In the 1970s, scientists placed extremely precise atomic clocks on airplanes and flew them around the world. When compared with identical clocks left on the ground, the airborne clocks showed a measurable difference, ticking slightly slower due to both their motion and the influence of Earth's gravity. The effect was tiny at the speeds of jetliners, but it was real and consistent with relativity's predictions. In particle accelerators, the effect becomes far more dramatic. Subatomic particles called muons, which normally decay in millionths of a second, survive much longer when moving at speeds close to light. Time for them stretches, allowing them to exist far longer than they would if at rest. The stretching of time also means that simultaneity, the idea that two events happen at the same time, is not universal. In our everyday lives, we assume that if two things occur together, everyone, everywhere would agree on their simultaneity. But relativity shows this is not the case. Consider two lightning strikes hitting the front and back of a moving train at the same instant. To a person standing on the ground, the flashes appear simultaneous. But to a passenger inside the train moving forward, the flash at the front seems to happen after the flash at the back. Both observers are correct in their frames of reference. There is no single, absolute agreement on what, at the same time, means. Time is woven together with space in a way that depends on motion, and simultaneity becomes relative. This relativity of time has profound implications for our picture of the universe. It means that the flow of time is not a single universal stream, but a collection of many streams, each tied to an observer's motion. What we call the present moment is not the same for everyone. In a sense, every observer carries their own unique slice of spacetime, their own version of now. This realization challenges our intuitive sense of reality, but is borne out by experiment and observation. Relativity also influences how we perceive distances. Just as time dilates, space itself contracts in the direction of motion when viewed from another frame. A spaceship traveling near light speed would appear shorter to an outside observer than it does to those inside. The passengers, however, would not notice any difference. For them, the ship feels perfectly normal, but the universe outside appears contracted. This interplay between time and space stretching in one direction, contracting in another ensures that the speed of light remains constant for all observers. It is as if time and space work together, adjusting themselves to preserve the ultimate speed limit of the cosmos. The relativity of time is not just a theoretical idea, but has real-world importance. Our modern world depends on technologies that must account for these effects. Consider the Global Positioning System, or GPS. Satellites orbiting Earth carry atomic clocks that provide the timing necessary to calculate positions on the ground. But those satellites are moving quickly relative to Earth, and also experiencing weaker gravity due to their altitude. Both motion and gravity affect the passage of time for their clocks, making them tick faster than clocks on the ground by about 38 microseconds per day. Without correcting for this discrepancy, GPS systems would drift out of sync, and your phone's navigation would be off by miles within a single day. The fact that your smartphone can guide you with such precision is living proof that time is relative and that Einstein's theory governs even our everyday lives. The relativity of motion and time also alters how we think about causality and the structure of events. Since observers in different states of motion disagree about simultaneity, the order of events can appear different depending on perspective. However, relativity preserves one crucial feature: causality. If one event causes another, like striking a match, and then seeing it ignite, that sequence is preserved for all observers. The light speed limit ensures that cause and effect remain consistent across frames. Though time stretches and bends, the arrow of cause and effect remains intact. When we extend these ideas to the universe at large, we see how relativity paints time as deeply interwoven with the expansion of space. Distant galaxies are not just moving away from us. They are being carried apart by the stretching of spacetime itself. Light from those galaxies travels vast distances, and the expansion alters how we measure time across billions of years. The deeper we look into the cosmos, the more relativity reveals itself as the foundation of our understanding, showing how motion and time are inseparably tied to the geometry of reality. The human scale. These effects are subtle, almost invisible. Our lives unfold at speeds far below the cosmic limit, in gravitational fields that are relatively gentle. Yet, the fact that time itself is relative, that two observers can live in the same universe yet measure different durations for the same sequence of events, tells us something extraordinary about existence. Time is not a universal backdrop, ticking the same everywhere. It is elastic, pliable, and subjective, woven together with space into the deeper fabric of spacetime. The relativity of motion and time invites us to rethink what it means to live in the present. Each moment we experience is not an absolute slice of reality shared by all, but a personal thread within the tapestry of spacetime. Two people walking side by side share almost the same flow of time. Their difference is imperceptible, but across cosmic distances, moving at unimaginable speeds or near massive objects, those threads diverge. The universe becomes a place of many times, many nows, each tied to motion and perspective, all coexisting within the grand geometry of spacetime. When we lift our eyes to the night sky, what we see is more than just a scattering of stars and galaxies. We are looking at a universe carried and shaped by spacetime itself. Spacetime is not just the invisible stage upon which cosmic events unfold. It is an active participant in the unfolding story. It stretches, it expands, it curves, and it dictates the very destiny of galaxies, stars, and the vast cosmic structures that populate the universe. To understand the cosmos is to understand spacetime, because every movement of planets, every orbit of stars, and every drift of galaxies across billions of light years is determined by the properties of the fabric they inhabit. In the earliest moments after the Big Bang, spacetime itself was compressed into an almost unimaginable density. The entire universe, with all of its energy and matter, was contained in a tiny region smaller than an atom. When the universe began to expand, it was not galaxies rushing outward into pre-existing emptiness, but space itself, stretching in every direction. This distinction is crucial, for it tells us that spacetime is not simply a container. It is dynamic. It can grow, evolve, and expand. The galaxies we observe today are not flying through space in the way a bullet moves through air. Instead, they are more like dots on the surface of an inflating balloon. As the balloon grows, the dots move farther apart, not because they are traveling across the surface, but because the surface itself is stretching. In much the same way, galaxies are carried apart by the expansion of spacetime. This expansion is measurable. In the early 20th century, Edwin Hubble observed that distant galaxies were receding from us, and the farther away they were, the faster they seemed to be moving. This discovery confirmed that the universe itself is expanding, that spacetime is stretching in every direction. What's fascinating is that no single point in the universe is the center of this expansion. Every galaxy sees the others receding, just as every dot on the balloon's surface sees the others moving away. This universal expansion is not an explosion from a central point, but the steady stretching of spacetime everywhere. The expansion also alters how we perceive light. As spacetime stretches, the light traveling through it stretches as well. Its wavelength elongates, shifting toward the red end of the spectrum in what astronomers call redshift. By measuring the redshift of galaxies, scientists can determine how quickly spacetime has been expanding over cosmic history. This stretching of light means that when we observe distant galaxies, we're not just seeing them as they are, but as they were billions of years ago. Looking into the depths of the universe is like looking into a time machine, with spacetime itself carrying the record of cosmic history encoded in light. This expansion is not slowing down. As one might expect from the pull of gravity, but speeding up. In the late 1990s, astronomers discovered that distant supernovae were dimmer than predicted, meaning they were farther away than expected in a universe slowing down. The only explanation was that the expansion of spacetime was accelerating. This surprising result suggested that some mysterious energy now called dark energy permeates spacetime, driving it apart at an ever-increasing rate. Dark energy remains one of the great mysteries of cosmology. But what is clear is that spacetime itself is dynamic and restless, shaping the fate of the cosmos. The geometry of spacetime at cosmic scales also determines the overall shape and destiny of the universe. If spacetime is curved like a sphere, the universe might eventually stop expanding and collapse back in a big crunch. If it is curved like a saddle, expansion could continue forever, but with a strange geometry where parallel lines diverge. If it is flat, as observations currently suggest, expansion will continue indefinitely, galaxies drifting farther apart, stars burning out, and the universe fading into darkness. These possibilities are written into the fabric of spacetime itself, showing that the cosmos is as much about geometry as it is about matter and energy. On smaller scales, spacetime weaves the cosmic web, the vast structure of the universe shaped by gravity. Galaxies are not scattered randomly but form clusters, filaments, and voids, all tracing the underlying geometry sculpted by dark matter and spacetime. Massive clusters of galaxies warp spacetime so strongly that they act as gravitational lenses, bending light from even more distant galaxies into arcs and halos. These lenses not only reveal galaxies too faint to see directly, but also provide maps of invisible dark matter, the unseen mass that makes up most of the universe. Spacetime thus becomes not just the backdrop of the cosmic web, but the sculptor of its form. Black holes, too, demonstrate how spacetime and the cosmos are inseparably linked. At the centers of galaxies, including our own Milky Way, supermassive black holes reside, curving spacetime so intensely that even light cannot escape. These objects, born from collapsed stars, or perhaps from primordial fluctuations in the early universe, anchor galaxies with their immense gravitational pull. The surrounding spacetime dictates how stars orbit, how matter accretes, and how energy blasts outward in powerful jets. Far from being cosmic oddities, black holes are central players in the evolution of galaxies. Their geometry interwoven with the destiny of stars and planets. Gravitational waves add another layer to this cosmic story. When massive objects like neutron stars or black holes collide, they send ripples across spacetime itself. Waves that travel at the speed of light and carry with them information about events billions of light years away. These waves are not vibrations in air or water, but oscillations in spacetime. Detecting them allows us to listen to the universe in a completely new way, tuning into the deep music of the cosmos as spacetime itself quivers with energy. In this way, the fabric of spacetime is not silent but alive with cosmic whispers that tell us about the most violent and energetic events in existence. Even the concept of cosmic horizons arises from spacetime. Because the universe is expanding, there are regions so far away that their light will never reach us, no matter how long we wait. These regions lie beyond the cosmic horizon, a boundary set by the age of the universe and the speed of light. The observable universe is vast, but it is not all that exists. Beyond the horizon, spacetime continues, carrying galaxies forever beyond our reach. This limit reminds us that spacetime not only carries the cosmos, but also defines what we can and cannot know about it. Some cosmologists wonder whether spacetime itself is infinite or finite. If infinite, the cosmos stretches without end, with galaxies extending forever in every direction. If finite but unbounded, it may curve back on itself, like the surface of a sphere, where traveling in one direction long enough could, in principle, bring you back to where you started. These questions are not just philosophical, but scientific. For the shape of spacetime determines the destiny of everything within it. The interplay between spacetime and the cosmos also hints at deeper layers of reality. Some theories propose that our universe is one bubble of spacetime among many, floating in a larger multiverse. Others suggest that spacetime might emerge from more fundamental structures, such as networks of quantum entanglement. If true, then spacetime is not the ultimate fabric, but a kind of woven tapestry emerging from even deeper laws. The cosmos we see would then be one expression of a reality more profound than spacetime itself. Yet, even as these mysteries remain, we can look up at the stars and know that spacetime is the grand architect of the cosmos. It carries galaxies apart, bends light across billions of years, guides planets in their orbits, and vibrates with the echoes of distant cataclysms. The night sky is not just a scattering of lights, but a living map of spacetime in action, a record of the universe's history written into its geometry. When we observe the cosmos, we are not simply looking outward, we are looking into the very fabric that shapes existence itself. Spacetime is one of the most successful concepts in modern science, a framework that explains everything from the fall of an apple to the orbits of planets, from the bending of light around massive stars to the rippling of gravitational waves across the universe. And yet, even with its profound successes, spacetime remains mysterious. It is like a vast ocean we have only begun to chart, an expanse where every discovery seems to open new questions. Scientists can describe spacetime with remarkable precision, but what it really is, at the deepest level, continues to elude us. One of the most enduring mysteries is whether spacetime is fundamental or emergent. We often picture it as the fabric of reality, the stage upon which all events take place. But in recent years, some physicists have begun to wonder if spacetime itself is not the ultimate foundation, but something that arises from more basic ingredients. Just as temperature emerges from the motion of countless atoms, spacetime might emerge from more fundamental quantum processes. Theorists exploring quantum gravity, the attempt to unify quantum mechanics with general relativity, suggest that spacetime may be woven from networks of entanglement, where information itself gives rise to geometry. In this view, the fabric of spacetime is less like a fundamental entity and more like a tapestry woven from threads we cannot yet see directly. Black holes sharpen this mystery. According to general relativity, a black hole is a region where spacetime curves so deeply that not even light can escape. But quantum mechanics adds a strange twist. Stephen Hawking showed that black holes should emit radiation, slowly evaporating over time. This creates a puzzle known as the information paradox. If a black hole evaporates completely, what happens to the information about the matter that fell into it? Quantum mechanics insists that information cannot be destroyed, but relativity seems to suggest it could vanish behind the event horizon. This tension between two of our most successful theories highlights the incompleteness of our understanding. Somewhere in the clash between quantum theory and curved spacetime lies a deeper truth about the nature of reality. The structure of spacetime at the smallest scales is another profound unknown. General relativity treats spacetime as smooth and continuous, a fabric that can bend and stretch, but has no smallest unit. Quantum theory, however, suggests that at unimaginably tiny scales, the Planck length, about 1035 meters, spacetime may not be smooth at all. Instead, it might be frothy, jittery, and granular, a kind of quantum foam where space and time themselves fluctuate wildly. If this is true, then the smooth geometry we experience is only an approximation, much like how the surface of the ocean looks flat and calm from a distance, but reveals waves and turbulence up close. We lack the instruments to probe such scales directly, but future experiments and theories may one day uncover the true grain of spacetime. Wormholes add another layer to the mystery. These hypothetical tunnels through spacetime, solutions to Einstein's equations, could in principle connect distant regions of the universe or even different universes altogether. Popular imagination has turned them into shortcuts for interstellar travel or even time machines. As we have drifted together through this quiet journey, we have followed spacetime from its first conception to its deepest mysteries. We began by asking a simple question: what is spacetime, really? And we found that it is not just a backdrop, not just a stage where the universe acts out its play, but a living, dynamic fabric that bends, stretches, and even ripples with the rhythms of the cosmos. We explored how space is more than emptiness, how it carries structure and form, guiding where and when events can occur. We reflected on time, the gentle current we each feel flowing forward, only to discover that it is not absolute, but woven into space itself as one dimension of a greater whole. Together, they form spacetime, the fabric of reality, the medium in which gravity is not a force, but geometry, shaping the orbits of planets, the bending of starlight, and the slow ticking of clocks. We traced how motion and perspective alter the passage of time, showing us that there is no universal now, but countless streams of time, each unique to an observer's path through the cosmos. We lifted our eyes to the stars and galaxies, watching spacetime itself expand, carrying the universe apart in its endless growth. And we considered the great mysteries that remain, black holes that guard secrets behind their horizons, wormholes that hint at shortcuts across reality, dark energy that drives the universe ever faster, and the possibility that spacetime itself may not be fundamental at all, but an emergent tapestry woven from deeper threads. In the end, what we have seen is that spacetime is not only the stage for the universe, but also one of its main characters. It sculpts the cosmos, dictates the paths of stars, carries the whispers of gravitational waves, and holds within it questions that reach beyond science into the philosophy of existence. It is both the most familiar thing we know, and the most mysterious. For every step we take in understanding only opens doors to deeper wonders. And so, as you rest, let the thought settle gently. You are not separate from spacetime. You are a part of it, shaped by it, carried by it, and inseparable from its unfolding story. The fabric of spacetime is the fabric of your own existence, stretching from the atoms in your body to the galaxies at the edge of the observable universe, binding all things together in the quiet, endless flow of reality.